Hi, this lecture is about atoms and molecules, but this is something a little bit different than the previous lecture. We're going to talk about how to read chemical formulas. We're going to talk about which chemical elements are important to recognize immediately. So in other words, when you see that chemical symbol, you know the name of that element. And we're going to talk about chemical equations, how to read a chemical equation. Let's start with talking about the elements for which you need to immediately recognize the symbol when you see them. You do not need to memorize the entire periodic table. So unless you're a chemistry major, no reason to do that. But there are some elements I want you to immediately recognize when you see them. And the first of those is carbon. Remember, all the elements are represented by a chemical symbol, and they all start with a capital letter. There could be a two-letter abbreviation for that element, and in that case, the first letter is capitalized and the second is not, and we'll see an example of that in a moment. So capital C, that is carbon. Carbon is incredibly important to recognize. You'll see it a lot this semester because it's the basis for all organic chemistry. All organic molecules are made mostly of carbon. And when we start talking about the big molecules that make up living organisms, you're going to see carbon a lot. H stands for hydrogen. O is oxygen. N is nitrogen. P is phosphorus. Okay, I'll go ahead and tell you, these are the ones you're going to see the most this semester. You'll sometimes see sulfur, especially when we look at proteins. You'll occasionally see sulfur. This is the main list. There are a few other ions that you should recognize because when we talk about transport across cell membrane and when we talk about ionic bonds, you're going to see these elements. So here's a good example of an element that has a two-letter abbreviation. Okay, sodium couldn't use S because sulfur was using S. So this is actually sodium. So again, capital N, lowercase a. Magnesium. Calcium. Potassium. Potassium is letter K because phosphorus was using the P. So again, no need to memorize the entire periodic table, but it is important to immediately recognize the most commonly used chemical symbols for this class. And again, carbon is the one you'll see the most. Now it's important to recognize how to read a chemical formula for a molecular compound and also how to read a chemical equation. So I'm going to start with this one because you have seen this one if you have watched the video on covalent bonds. This is the molecule methane. It is an organic molecule. And it's important to recognize what we mean when we write CH4. So first, important to realize that this 4 is a subscript. Kind of hard to see that when I write it on the screen. But that 4 is only telling you something about the hydrogen. It has nothing to do with the carbon. Also in chemistry, we don't write a 1. So there's no 1 written in front of this molecule and there's no 1 written by the carbon. But we assume if there's no number there, it's a 1. So this is telling us that this methane molecule is made up of 1 carbon because there is no number after the carbon, and 4 hydrogens. And these are all bonded together to form this molecule. Let's look at another one. Let's look at water. H2O, and most of you know the chemical formula for water. Again, the subscript number is only telling you something about the hydrogen. So this is telling us we have 2 hydrogens bonded to 1 oxygen. Again, we don't write a 1. So we assume that since there's no number after the oxygen, that is 1 oxygen. What if we had 6 H2O? That big number 6 in front of the water is telling us we have 6 water molecules. And if we count the total number of hydrogens and the total number of oxygens in those 6 water molecules, we see that they're almost imaginary parentheses here. So that 6 gets multiplied by everything after it. So 6 times 2, that means we have 12 hydrogens making up these 6 water molecules. And 6 times 1, 6 oxygens. Again, I know that's a 1 because there is no number there. And if there is no number, we assume that's a 1. We do not write the 1 in chemistry. It's also very important to realize that the reason it's written this way, the reason it's not written H12O6, that would be something totally different, and I'll show you that in a minute. The reason it's written as 6 H2Os is because here's what we really have. It's telling us we have 6 of these, and I am going to take the time to draw all 6 of them so I can really illustrate this point. These are 6 separate water molecules. They are not all connected through covalent bonds. You're going to see when we talk about hydrogen bonds that they do actually connect through hydrogen bonds, but that's not sharing electrons. So we're not joining these through sharing of electrons. We don't write them all together. So if we had written H12O6, that would be a crazy imaginary molecule that doesn't exist, but that would tell you you have 12 hydrogens bonded to 6 oxygens. This is telling you something different. Okay, there are 12 hydrogens total and there are 6 oxygens total, but they are all separate H2O molecules. And if you counted all the hydrogens, you would see there are 12, and if you counted all the oxygens, you would see there are 6. So that's telling you something very different than this. This would tell you there are 12 hydrogens and 6 oxygens bonded together. Again, that doesn't exist, but just speaking hypothetically. But this is telling you have 6 separate water molecules. Very important difference. Okay, now let's look at a chemical equation. Let's look at chemistry happening. And I'm going to give you the chemical equation for cellular respiration, the most important chemical reactions that take place in your body. So this general formula that I'm going to write is really just the general synopsis of what happens. You're going to see when you learn about cellular respiration, this is a very complex, multi-step process. This is a metabolic pathway. It doesn't just happen all in one step. But I like drawing this general chemical formula because it's a really good example of how to count the number of atoms on each side of the chemical equation and really seeing a good example of that. Okay, I'm going to have to write this a little smaller because I have to fit the whole thing on here. So C6H12O6. So these are all subscript numbers, plus 6O2, and then an arrow, very important, 6CO2 plus 6H2O. Okay, the H2O you already know, we just saw that. This is glucose, oxygen, carbon dioxide, and water. A couple of things that are really, really important about this. This arrow is showing you the direction in which this chemical reaction is proceeding. So this is the direction of the chemical reaction. It's moving from left to right, and it's moving from what we call reactants to what we call the products. So the reactants are on the left side of the arrow, and the products are on the right side of the arrow. So in this reaction, we would say glucose and oxygen are the reactants, and carbon dioxide and water are the products. If we went through and counted the number of each type of atom on the left side of the arrow, it always has to equal the number on the right side. And I'm going to show you exactly what I mean by that in a second. But what's really amazing about chemical reactions is we're never creating matter and we are never destroying matter. So matter is never created or destroyed in a chemical reaction. This is a very important point in chemistry, and it's often called the law of conservation. Of matter. This is also going to be important from an energy standpoint when we really start looking at the energy involved in different chemical equations, in different chemical reactions. In cellular respiration, it's going to be especially very, very important, looking at how we extract the energy from glucose and use that to drive chemical reactions in the cell. Very, very important. The reason it's important to realize that matter is never created or destroyed is it's important to recognize all we're doing in chemical reactions is usually breaking bonds, taking those atoms and rearranging them to form something else. But none of them go away, okay? None of them are lost. We also don't bring anybody new into the party. So if we look at the number of each type of atom on the left side of the arrow, it needs to always equal what's on the right side of the arrow. So let's look at who we have involved here. Carbon, hydrogen, and oxygen on the left side. Okay, and on the right side, we have carbon, hydrogen, and oxygen. So already you can see there are no new players on the right side. Everybody who is on the left side is still on the right side. Nobody left, nobody came in, everybody's the same. Now we need to count the number of each, and those need to be the same too. And if they're not, then you have to do something to balance it. Now, I will go ahead and tell you, we will not be balancing chemical equations in this class. You'll be happy to know. If you take a chemistry class, you will be balancing chemical equations. But I want you to recognize all we're doing is breaking bonds and rearranging those same atoms to form something completely different. And you can recognize that just looking at this equation. Glucose and oxygen, very different from carbon dioxide and water, but they are made of the exact same atoms. That's pretty crazy to think about. So let's do some counting. This is a really good practice for reading these chemical formulas. Again, subscript numbers only relate to what they follow. So looking at glucose, this 6 is only related to the carbon, the 12 is only related to the hydrogen, and this 6 is only related to the oxygen. Okay, so that's telling us we have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. Okay, but that's just in the glucose. We also have something else on the left side of that arrow, and that is oxygen. We have 6 O2s. So that's saying we have 6 of these, oxygen, and it happens to be double bonded. You wouldn't know that from looking at this, but you would know that by drawing the electron configuration and figuring out how oxygen has to share with another oxygen. That was the topic of the previous lecture on covalent bonds. But you have 6 oxygens bonded together. So you have 6 separate O2s, which means you have 12 oxygens total. So we're going to add 12 to this. Okay, again, where did I get 12? Remember, this is imaginary parentheses. So that 6 gets multiplied by 2. In other words, if we drew out all 6 of those O2s, sorry, I'm drawing this very sloppily so you can just get the point here. So there's all 6 of my O2s. That's 12 oxygens total. So 6 plus 12, that means we have 18 oxygens on the left side of that arrow. So in our reactants, we have 6 carbons, 12 hydrogens, 18 oxygens. Let's count what's on the right side. Okay, carbon dioxide. Again, this 6 gets multiplied by everything after it. So it's going to be 6 times 1, that's 6 carbons. 6 times 2, that's 12 hydrogens. Oops. Sorry. Goodness. 6 carbons and 12 oxygens. Okay, let's go on to water. Again, imaginary parentheses here. 6 times 2, and this is exactly how we did water before, so you should already be able to do this one because we just did it in the example above. 6 times 2, that's 12 hydrogens. Okay, and we're going to have some more oxygen here. 6 times 1, that's 6. So that equals 18 also. So 6, 12, 18, 6, 12, 18. Awesome. So we have the exact same number and the exact same kind of atoms on the left side of the arrow as we have on the right side of the arrow. Very, very important. You will also be looking at compounds which come together through ionic bonding. So if you see something like this and it's written together, this is actually a compound, and this is showing you that there's a sodium that was attracted to a chlorine. And those are connected just through an attraction. So this is more, whoops, where's the camera? Okay, sodium and chlorine, ionic bonding. They have opposite charges, so they're attracted to each other. Remember that when they're separate, they have a charge, which is written with a superscript. So the sodium ion has a positive charge and the chlorine ion has a negative charge. They're attracted to each other, and when they're connected, the positive one and the negative one cancel each other out. Remember, that's different than the covalent bond. So when we look at hydrogen bonded to hydrogen, H2, that's shown as a line, and that is a covalent bond. This attraction between ions of opposite charge, that's an ionic bond. So that should review from the 2 bonding lectures. And then, of course, real quickly going back up to the waters we drew. If you haven't watched this yet, this is a sneak preview. If you have watched it, it's review. But remember, neighboring water molecules are weakly attracted to each other through hydrogen bonding. So all of these oxygens and hydrogens of neighboring water molecules are going to be weakly attracted to each other. We show that with 3 dots, and that is a hydrogen bond. And I won't go into any more details about that in this lecture. You should watch the hydrogen bond lecture for that. Okay, that's all. Thanks.